All right. So again, the goal today is to overview chapter 6 and 7, which means overviewing statistics, the basics of descriptive statistics. However, being a more advanced class, we do want to get into the theory that will help us ultimately apply the statistics that we're learning, which does mean we'll continue to use probability theory along the way. Advanced statistics is dependent on probability theory, and you could say advanced applied statistics is ultimately dependent on probability theory. So wherever that seems relevant, we will continue talking about that. So we'll ground this in the context of an example, and the example will be the Chutes and Ladders example. So we did the Chutes and Ladders simulation the other day, last week. By the way, gotta say this, I hope you realize today is 2/22/22, right? You want to maybe celebrate at 2:22 p.m. And do something special. Anyway, coming back to math, this was the Chutes and Ladders simulation in Mathematica. Again, this was code that essentially deals with the chutes and the ladders, chutes being slides. This is code that does the spinning and moving. This is code that combines those to do what I call the full turn, where you spin, move, and possibly go up a ladder or down a chute. And then we can generate data with nest list or nest while list. And if you use, nest while list along with table, you can generate, in this case, 1,000 simulations. The fact that I have 1,000 here means I'm doing 1,000 simulated games. I could make it 10,000 if I wanted to. And if I go ahead and enter the number of spins data, I see 1,000 numbers. That represents, again, 1,000 simulated games. How many spins did it take to get to the end to win the game? Of course, you're really only doing one player here instead of two. But you could play Chutes and Ladders by yourself if you wanted to, just for the sake of seeing how long it takes you to get to the end. So there's 1,000 numbers there, 1,000 data points. This is statistics. We've gathered some statistics from some unknown random variable. There's a random variable X that would represent the number of spins to win the game. X has some distribution. The point of the simulation was that it's not clear how to approach the distribution of X theoretically, because how do you deal with the chutes and the ladders? They're in kind of weird spots and they have strange lengths. There seems to be no clear way to deal with that theoretically, and so simulation seems to be the way we've got to go. Once we've got these data, as in chapter 6, we can make graphs of these things, a histogram showing what happened, right? There's a descriptive statistic kind of thing, a graph, a histogram showing you that, for example, with those 1,000 games, I don't know if you can see that number there, but it says there were 8 games that were in this range, which it's not clear from the labeling here, but I'm guessing that looks like maybe 4 to 10 spins to win the game, 8 out of 1,000. Those were games where it was won very quickly. 103, you can see that bar goes up slightly above 100. We're in the range of somewhere in the ballpark of 10 to 15. I guess the labeling here is maybe every 5. 142, we're in the range of 15 to 20 spins to win the game. The modal number of spins to win the game was in the ballpark of 20 to 25. That's the highest bar, at least as a group of numbers. That was the most common kind of number of spins to win the game. But this does have ultimately a long right tail. It's a skewed distribution. So we should expect the mean, the average, to be bigger than 20 to 25. And if we go ahead and calculate it here, well, let's see. Using mean, these data I labeled number of spins data. It should be in the ballpark we've seen of 29 to 30 or so. Yeah, 29.771. We could also do the standard deviation of the number of spins data. And that, for this particular run, is about 14.1. Square that, you'd also get the variance. Though you might wonder, is this the sample standard deviation and the sample variance that you've learned about in prob and stats, where you have to divide by n-1 instead of n? Remember all that? Let's go ahead and talk about that now. And we ultimately want to relate this to what we're seeing here. And my ultimate goal is to also try to relate the probability, in particular, you know, a right skewed distribution like this, what kind of distributions do we know that have a PDF that has that kind of shape? How about a gamma distribution? Remember the PDF for a gamma? I'm sure you don't, because it's complicated. I don't remember it either. I've got to look it up. Gamma distribution has a probability density function that looks like this. Effectively, it's a constant for a given value of alpha and a given value of beta. It's a constant times x to a certain power times an exponential decay, where the constant is this funny thing because the integral of this thing involves the capital gamma function. It's related to the definition of the capital gamma function. There's the capital gamma function, or just the gamma function for short, but yeah, that's the Greek letter capital gamma. It's a function of the parameter alpha. It's an integral with respect to z, but this integral involves alpha. When you do the integral, the answer depends on alpha. It is related to the factorial function, gamma of alpha, because this fact ultimately leads to the fact that gamma of alpha is alpha minus 1 factorial. For example, gamma of 4 is 3 factorial, 6. Gamma of 5 would be 4 factorial, 24. It's related, it's a generalization of the factorial function, and to make this integrate to 1, as you integrate z going, or x going from 0 to infinity, you've got to use this constant in front. So my goal here today is, as I talk about the theory from chapters 6 and 7, is to see if I can figure out a value of alpha and beta that will make this PDF's graph fit these data. In fact, I could even do it initially here with just effectively some experimentation. The PDF, what I could do, this plot I've labeled hist for histogram, is I could try combining that plot, histogram, using show, and a plot of, well, probably I need to multiply the PDF by some scaling factor to make sure it scales up high enough. But in Mathematica, here's code to get the PDF. You don't even need the formula. A PDF of whatever your distribution is, I'm going to use a gamma distribution, not grandma, but gamma distribution with parameters alpha and beta. What should I pick for alpha and beta? That's the hard part. I don't know, just try something to start with. How about, I don't know, alpha is 5 and beta is 2. Try 5 and 4 maybe. And I'm thinking about the fact that alpha times beta is actually the mean. Maybe, okay, maybe I should do 5 times 6. This is alpha, this is beta. The meaning of alpha and beta is not clear. They're just distribution parameters. They just affect the graph in some mysterious way. Although we do know, if you look in chapter 4, that alpha times beta is the mean. I know the mean of the data is close to 30, so why don't I just try 5 and 6 and see what happens, since 5 times 6 equals 30. This is a function of x, say. X going from, in this graph here, say 0 to 100. Let's make it easy to see by doing plot style, say thick blue or something. We won't see it because it's going to be too low. But maybe if I multiply it by 100 or something, maybe that'll be enough to see it. Maybe. Or maybe okay, let's try 1,000. Okay, this kind of thing happened before class too. When I was trying this. Why are we not seeing it here? Let me try the lower values. Okay, this is happening. I did it before class. I was having trouble before class, but I did get it to work, so I'm not sure why it's not working now. Maybe let's just plot this by itself here. Why is it not plotting? Oh, because the 1,000 needs to be outside, that's why. There we go. Okay, that's better. Yep. Yeah, the 1,000 needs to be outside the PDF. Okay. Interesting. Why is it cutting it off there? Let's try this. Plot range all. Mathematica is weird sometimes. There we go. That's better. Let's go back to the 6 and the 5. Maybe multiply by 3,000 instead of 1,000. That's looking halfway decent. Looks like alpha equals 6 and beta equals 5 is a halfway decent approximation to 2 parameter values that's fitting these data reasonably well. And this is the approach many people take to this kind of thing if they're on a job and they're trying to fit data to some distribution, and they just do trial and error. That's not a very scientific approach. We do want to try to take a little bit more scientific approach, you might say, to figuring out what alpha and beta should be. Okay, and that's going to be part of the point of what we talk about now. So let's now get into the main content. I'm not going to give official long-winded definitions and theorem statements. They are in the book. You can read them. Mostly I want to remind you of ideas that you've learned about in the past in problem stats. So what's the background? The background is we've got some population. This is the background of doing inferential statistics. You got some population that you want to know about. You can't study the entire population. You need to study a sample. Now, usually when people think about populations and samples, they're thinking about real life populations and samples, like populations of people and samples of people, or maybe populations of companies and samples of companies. And that's all fine and good, and that's usually good for most people's purposes, but we are in an advanced applied statistics course, so we're doing things a bit more theoretically, not for no reason, right? We have good reasons for these things, and ultimately, for one reason today, is we want to understand best ways, more scientific ways of estimating the parameters like alpha and beta. That should be in the back of your mind as a goal. But you can't just sample willy-nilly. You can't use bad sampling techniques is what I'm trying to say. It needs to be some sort of random sample, ideally. To be a bit more specific, when you're actually doing sampling in real life, you want what's more officially called simple random sampling. Effectively, if it's people that you're sampling, you're putting the names in a hat, so to speak, or maybe a virtual hat, and you were drawing out using some form of randomness. If it's a hat, a literal hat, you're shaking it up, putting your hand in there, mixing it up before you grab somebody's name and say you're the first person in my random sample. Of course, it's usually done more by computers these days. However, we're thinking about this still a little bit more theoretically. We're really thinking of the population as really being more related to a random variable. The population, in effect, represents all data that you would get, infinitely many data points, say, for some maybe continuous random variable like a gamma distribution. This kind of corresponds to the random variable that we are studying. And the random sample, which, yes, in real life, you can actually sample people or companies or whatever, but we're thinking about it a bit more theoretically as being effectively a list of random variables, x1, x2 through xn. We're making the assumption, and this is the randomness. This is related to the fact that we're doing simple random sampling. We're making the assumption that these are independent. These are independent. When we do the theory, we make that assumption. When we try to apply the theory, we ask whether the assumption seems reasonable. Doing the theory, you make the assumption. When you apply the theory, you ask does the assumption seem reasonable with the same distribution as X? That's what a random sample is for us. So when I say the same distribution as X, I mean they have the same PDF for a continuous random variable, PMF, probability mass function if it were a discrete random variable, means they have in either case the same CDF, same mean, same variance. They are effectively the same random variable, but we're taking them as being unrelated in their values, independent. The value that one takes on when I perform the experiment doesn't affect the value that the next one takes on, etc. It is a theoretical kind of assumption to make. And to be real technical about it, what it really means, related to chapter 5, is that the joint PDF of the not bivariate random variable, not trivariate random variable, not quadvariate random variable, but n-variate. I'll call it the n-dimensional random variable, put x1 through xn inside parentheses. Effectively, this is a vector written as a point. I could write it as a point, or effectively think of this as a row vector. I could also write it as a column vector. And by the way, we will be dealing with vectors a lot in this class once we get past spring break into April. Doing multiple regression, we'll be dealing with vectors and matrices. Your linear algebra will come in handy. The joint PDF, which you might label little f sub x1, x2 through xn, and we don't typically bother putting the commas in there, of little x1 through little xn. The independence means we are assuming that that joint PDF is the product of the marginal PDFs of each variable individually. And since these random variables, capital X1 through capital Xn, all have the same distribution, they all have the same distribution as X, all these little f's over here are actually the same function. So effectively, these are all f sub x, x's. Though I am plugging different variables into them. So I can't write f sub x to the nth power. So the same distribution as x means that that equation is true. So it's an assumption we're making in the theory. Now, for us, we are, yes, an advanced statistics course with a fair amount of theory, but we're not super advanced. We're not graduate level. And so for us, we don't really have to deal with this too much. But I wanted to mention it so that it's in your mind as something that in reality is in the background. And I think we will deal with this, at least in the case when the sample size n is small, like n is 2, for example. In fact, we already dealt with it one day, a couple weeks ago, when we talked about the distribution of x1 plus x2, and I drew a square and I drew shaded some areas in the square. We were talking about the distribution of x1 plus x2. I think x1 and x2 were uniform. In that situation, we were effectively dealing with this kind of situation when n was 2. I did assume x1 and x2 were independent. So that's the background theory that we're not going to get a ton into. We're going to get into other theory. The theory of estimators of parameters. The random variable x, the population, has parameters that are associated with it. Unknown parameters. Like what? How about like the mean mu? Or the variance sigma squared, or the standard deviation sigma? Or maybe even a median. We haven't really talked about medians in here. I think I will try to emphasize medians some now. A little side notes here. For if x is a continuous random variable, we know the mean. You don't have to write this down. We know this. We know the mean, the expected value of x, if x is continuous, is an integral in general over the entire real number line of x times the PDF. Call that mu. Greek letter, mu. It's a population parameter. It's a number. What would the median be? Maybe we should call that M for median. It doesn't really have an equation that defines it. It really has, well, an explicit equation. You have to solve an equation to find the median. It's defined by the equation capital F of little m equals 1/2. You're looking for the value, a number, little m, that makes the CDF equal to 1/2 at the median. In terms of the PDF, again, we are in the continuous case here. If the PDF, for example, looks maybe right skewed like a gamma, the mean is the center of mass. The mean is going to be, okay, I made it kind of way out there, but the mean might be there. The median in such a situation is going to typically be smaller. The mean is the center of mass. Center of mass is what I'm writing here. The median is sometimes called the middle value. And it's constructed so that the area under the PDF to the left of the mean is 0.5, and the area under the PDF to the right of the median is 0.5 of the median. The center of mass is where to put a little fulcrum to make it balance. The middle value is where half the area is to the left and half the area is to the right. Of course, if the distribution is symmetric, like a normal distribution, then there's the same thing, the median and the mean. The mode is, for a continuous distribution like this, the location or locations where the highest value of the PDF is, where the probability density is greatest. That would be the mode. I'm not really going to get into the mode, but we could. So populations have parameters like the mean, median, standard deviation, variance. Maybe if we got into third and fourth moments, we talk about skewness and kurtosis and things like that. We won't. Those will all be population parameters associated with the random variable that we would like to learn about. The goal is to learn about the random variable, because that's learning about the population. The random sample helps us learn about the population. The random sample has associated with it statistics. When you say the word statistics to somebody off the street, they say, oh, no, I don't want to take statistics, right? They're thinking about a class. If they've actually taken statistics, most people think about statistics as being, well, these are numbers you compute. Well, okay, like a mean if you have to pull teeth. Oh, yeah, I guess I remember computing a mean in my stats class. Or maybe even a standard deviation. So they're thinking about them as being numbers. For us, in a more advanced statistics class, we're thinking about these things more theoretically. we're thinking about statistics as being random variables, but not any old random variables. They're random variables that are generated from a random sample from the population. So for us, a statistic is a random variable which is a function of a random sample. Where a random sample is what I told you 10 minutes ago, is a collection of n random variables that are independent and have the same distribution as the random variable that we're studying from the population. A random variable, a statistic is a random variable which is a function of a random sample. I didn't really fully state this sentence in the best way. I should have said a statistic is. Statistic is a random variable which is a function of a random sample. Kind of an abstract definition. How does this play out in practice? Well, for example, the sample mean, x bar, make it a capital X, is a function, call it h, of x1 through xn. What is h? It's the function that tells you to take the inputs, add them up, and divide by how many there are. That's what the function is. Or with summation notation, factoring out dividing by n as multiplying by 1 over n. 1 over n times the summation I goes from 1 to n of capital X sub I. That's our most famous statistic, the sample mean. We also have the sample variance. S squared, right? Capital S squared is the symbol for the sample variance, not sigma squared. What was that? By definition, if the summation I goes from 1 to n of essentially intuitively, variance is supposed to measure dispersion, spread. So intuitively, we want this to be something big when the values of x are spread out and something small when they're not so spread out, when we actually observe values. Capital Xi minus capital X bar measures the distance between Xi and X bar, positively or negatively. If I average those numbers, you'd get 0, right? You average those deviations from the mean, they're called, you're in general going to get 0. So to avoid that, we end up squaring them. And we want an average version of this. The temptation is to divide by n instead of n minus 1, but no, we divide by n minus 1. Why? Why do we divide by n minus 1 instead of n? The reason is very technical. It helps make S squared and what we call an unbiased estimator for sigma squared. Sigma squared is the population variance, unknown parameter, a number. This thing is a statistic. Being a statistic means it is a function of the random sample. It is a random variable. It's got a distribution. It's got a PDF. if it's in the continuous case, a PMF, if it was the discrete case, it's got a CDF, it's got a mean, it's got a variance itself, the variance of the variance. It's got a standard deviation, all those things. I'd be interested in knowing its distribution. And the fact that it's unbiased means something special about its mean. Does anybody remember what that would mean? X bar is unbiased as well. Maybe we should do it for X bar. Anybody remember what it means for X bar to be unbiased? You can say it in words using the word mean 3 times. I can say a phrase using the word mean 3 times that exemplifies what it means for X bar to be an unbiased estimator for mu. You're right. The mean of the mean is the mean. The mean, expected value, of the mean, X bar, is the mean, mu. That's not a crazy equation. That's a very fundamental equation. It means X bar is an unbiased estimator for mu. What is mu? First of all, mu is a population parameter. It's the mean of X. Remember, X is the background random variable that we are trying to study, that we are trying to learn about, that we're trying to model, you might say. It's got a mean, we would hope at least. Actually, means don't have to exist. It's possible for little f to be a PDF and integrate to 1, whereas the mean, this integral, actually might not converge. Might be an improper integral that diverges. That's possible. I haven't shown you any example, but it's pretty easy to come up with examples. So assuming mu exists, that integral in the continuous case converges, that's a number, that's a population parameter, and it is the mean of X, the mean of the population. Expected value is a theoretical mean, expectation. X bar is also kind of a theoretical mean. It's a sample mean. It's more specifically a statistic. It's a random variable. E is not a random variable, right? It's an operator. You take E of something just like you take the derivative of something. E does represent a theoretical taking of means, you might say. X bar is a theoretical sample mean. It's this function of the random sample. It is a random variable. It's got an expected value. That expected value is a number, and it happens to be the same number as the mean of the population. Sample variance is also an unbiased estimator, but not for the mean, but the sample variance, sigma squared. S squared is an unbiased estimator. For sigma squared. What's sigma squared? Sigma squared is the population variance. Variance of X, the random variable. Which, if the random variable is continuous, you'd compute sigma squared by doing integrals, right? You've found the mean, E of X, the expected value of X. You'd have to find the second moment, E of X squared. And you'd have to do a computational formula for the variance, E of X squared minus E of X quantity squared, right? We talked about that kind of stuff a lot, or you've used that at least. That's a number. S squared's not a, X bar and S squared are not numbers. They're random variables. Which, again, I've hinted at, if you did graduate level statistics, that means they're really functions. certain special kinds of functions, but we're taking a more intuitive approach. They're still abstract. We're just thinking of them as abstract quantities that can vary according to some model, some PDF. We can use the model to estimate probabilities that they take on certain values. As random variables, they have means, they have expected values. What are those expected values? This and this. Proving this one's pretty easy. You can find it in chapter 7. Pretty easy proof using properties of expectation. Proving this one's actually pretty difficult. It is in the book, in the appendix. I showed this to you if you were in Problem Stats last fall. I don't remember about the fall before that. Probably showed it to you. In the appendix, it involves some pretty crazy calculations. Where is it? Why can I not find it? I'm not finding the appendix where it is. I found the answers. I'm in some trouble today. There it is. Okay. Page 782 and 780, mostly 783. Essentially, those are the calculations that prove S squared's unbiased. Yikes. Now you can wade through these calculations and verify every step. And if you want to, more power to you. I have done it. I verified every step. And you get the right answer in the end, but it's like, okay, why? It doesn't provide much intuition. This is like symbol pushing using properties, right? It doesn't provide much intuition. Simulation still may not provide intuition, but maybe could help us believe it at a more gut level of why this works, or that it does work. Won't do that simulation today, but maybe on Thursday. Because again, today we want to get a more broad overview. Can I clarify anything? It's theoretical, but we will apply it. When we do, mostly after spring break, a little bit today and next on Thursday and next Tuesday, but mostly after spring break, we'll get into applications. The applications ultimately really are mostly related to confidence intervals and hypothesis testing, which we've done before, but we'll do in more depth now in this class. Let's provide a little bit more detail about the distribution of X bar. One thing we know about it is it's unbiased, so this is true. What else can be derived about it? Well, maybe we can compute its variance. What is the variance of the mean? So what is the mean? It's this. Expectation E, capital E, the expected value operator, has nice theoretical properties. It's a linear operator. If we were taking E of this, we could bring the 1 over n out in front of the E. And we could also take E of a sum by doing the sum of the E's. Can we do that for variances? Kind of, but with some caveats. If I pull the 1 over n out in front, that's okay as long as I square it. So that's a property of the variance operator. It's not a linearity property, but it is a property. And it's tempting to then say, maybe now I should pull the summation out. Can I do that? I'm going to go ahead and do it, seemingly implying that you can do it. But can I really? I must be able to. Why else would I write it? Well, sometimes I write things just to illustrate that they're not true. I could put a big X through this. But this is true if we make an extra assumption. What's the extra assumption? And we did make the assumption already, actually. What does your gut tell you? What do we always assume when we're doing theoretical prob and stats here and we're dealing with like more than one random variable at a time? Independence, right? We're always assuming independence. You've been doing that in homework for the past 4 homework assignments or so. We're assuming they're independent because it makes the theory so much easier. Not that it's easy, but so much easier than it would be if otherwise. And then when you again apply the theory, you hope it seems reasonable to assume independence. Can't really prove independence in most practical situations. You just say, yeah, it seems reasonable. I've got data that makes it even seem reasonable, maybe. So this is by independence of the random sample, of the variables in the random sample. That's what a random sample is. You got independent random variables from the same distribution. And they do all have the same distribution. So even though a priori these variances could be different, in fact, they're all the same. Got a bunch of sigma squareds. Each xi has the same distribution. The distribution of x itself, the population variable that we're interested in learning about. So I'm really adding up a bunch of constants. How many of them? N of them. Cancel one of those n's and you get sigma squared divided by n. The variance of the sample mean, x bar, is the population variance divided by the sample size. Ringing a bell? You remember this from prob and stats? And moreover, that's a good thing. How is it good? That's a quantity that goes to 0 as n goes to infinity. In other words, I can make the variance of x bar for a given situation as small as I like by taking n sufficiently large, by making sure I pick a sample size sufficiently large. Think about this in terms of target practice. The fact that x bar is unbiased. Here's my drawing of a target with a bullseye. The fact that x bar is unbiased means on average you're going to be around the bullseye. But your spread could be large. If n is not very big. So, you know, I drawn a bunch of points that on average are close to the bullseye, but each individual one could be far away. The fact that the variance of x bar is this means that when n is large, there's not going to be very much variability. Now, if x bar were not unbiased, if it were biased, then you could have low variability, but be far from the bullseye, right? You could be hitting up there. When it's both unbiased and has small variance for large n, you are going to be both averaging around the bullseye and be near the bullseye. The bullseye is where the population parameter value is. Since the variance of x bar is sigma squared over n, the standard deviation of x bar, sigma sub x bar, would be the square root of the variance of x bar, which would be the square root of sigma squared over n, which is going to be sigma divided by square root of n, which also goes to 0 as n goes to infinity, though not as fast. Especially once n gets really large or sigma is fairly small. I mean, you take the square root of a number that's, if sigma squared over n happens to be, if n is large enough to make that less than 1, then the square root's actually going to be bigger. So yeah, in asymptotically speaking, it doesn't go to 0 as fast. The fact that the variance and the standard deviation here go to 0 as the sample size gets larger means that, or implies that x bar is what's called a consistent estimator. For mu. That definition you don't find in the book. In fact, this is not really the definition of consistent estimator, but it's related to it. The fact that these things go to 0. I will give the more official definition of consistent estimator either Thursday or next Tuesday, and it will be something to know for the test, something extra, a supplemental kind of thing to know. But this is a consequence of consistency, or it's related. When this happens in a certain situation, it will be a consistent estimator. So unbiased and consistent, those things sound good, right? You don't want to be biased. You'd like to be consistent. Those things sound good, and they are good. You want your estimators to satisfy those properties. In section 7.2, you get into how do you find estimators? How do you figure out what estimators should be? By the way, when I say the word estimator, that does refer to the random variables, x bar, s squared, that we are using to estimate population parameters when we observe their values based on a random sample, an actual random sample that you have numbers with. So x bar and s squared and s are the most common ones. I should mention that just because s squared is unbiased for sigma squared does not mean s is unbiased for sigma. You can't take the square root of both sides here. Or more officially, you can't take the square root of this thing and think it equals E of s. It doesn't. We'd like to come up with some methods for figuring out good estimators. Like, okay, let's finish class the last 20 minutes here by going back to the example with chutes and ladders and the gamma distribution. So let's say X has a gamma distribution with parameters alpha and beta. For chutes and ladders, that data, it's just an assumption to make. I don't know for sure that X truly has a gamma distribution. Probably the gamma distribution of the number of spins to win chutes and ladders is not some well-known distribution in reality. Perhaps it's even undescribable in terms of relatively simple math. So when I say I'm going to use a gamma distribution to describe it, what I'm really doing is I'm making an assumption. I'm modeling. It's mathematical modeling, statistical modeling. I'm assuming it has a gamma distribution. And if I make that assumption, what should alpha and beta be? Those are population parameters for a gamma distribution. And I'd like to estimate them based on data. Which means I need estimators for those things. They're not the mean and the variance of the gamma distribution, but they are related to the mean and variance. In chapter 4, it's derived that the expected value of such a distribution, mu, E of x, is going to be alpha times beta. And the variance of such a random variable, such a distribution, is going to be alpha times beta squared. In chapter 4, look at the table in chapter 4. We're on the page where the gamma distribution formula was, or shortly thereafter. Derived in the book, or hinted at being derived using the Mohn generating function. E of x is alpha times beta, variance of x is alpha times beta squared. So they're related to mu and sigma squared, but they don't, alpha and beta themselves individually are not mu or sigma squared. Can I come up with estimators for these things? Yeah. Intuitively, you could look at these equations and say, well, you know, if I pretend mu and sigma squared are, if I pretend those were known, I could solve this system of equations for alpha and beta in terms of mu and sigma squared. But would that be useful? Because I don't really know what mu and sigma squared are. It would be useful if I replaced mu and sigma squared with natural estimators for those things based on moments. And this leads to the method of moments. We want to find the method of moments estimators for alpha and beta. The kth moment of x, by definition, is the expected value of x to the k power, right? First moment is the expected value of x, the mean. Second moment is the expected value of x squared. It doesn't equal the variance, but can be used to find the variance. Third moment is the expected value of x cubed, which you could use to describe skewness, it turns out. In general, this is the kth moment of x. It is a population parameter. This is an unknown population parameter. A natural estimator for the kth moment we could call m sub k is just to average the observed values of the x to the k powers based on a random sample. Add up xi to the kth power and divide by n. It's a mean. You're averaging not the xi values themselves, but the xi values to the kth power. That's a statistic. This one is a parameter. It's a fixed but unknown number. This one is a statistic, a function of a random sample. Which then means it itself is a random variable. What you do with the method of moments is you replace these population parameters with how they're related to the theoretical moments. For example, mu gets replaced with M1, which really is X bar. And sigma squared gets replaced with, use the shortcut formula, the second moment minus the first moment squared. And then solve that system of equations for alpha and beta. And that's a good thing because we can find observed values of moments. We can find observed values of statistics. We can't find parameter values if we don't know what the distribution is. We're trying to estimate the parameter values. That's what we do. Okay, so this first equation, mu gets replaced by M1, which is X bar. I could write in X bar if I wanted to. The book uses M1. Equals alpha times beta. And then replace sigma squared with M2 minus M1 squared. See where I pointed there? M2. Replace E of X squared with M2. Minus M1 squared. Replace E of X with M1. E of X squared does not equal M2. I'm not saying it equals M2, and E of X itself does not equal M1. I'm replacing these parameters by natural estimators, which are statistics. They're not equal, but it's a logical replacement to make for this method. So M2 minus M1 squared is what sigma squared gets replaced by. So solve this system of equations now for alpha and beta. It's a nonlinear system. In general, that could be difficult to solve. In this case, it's not too hard. For example, I could solve for beta pretty easily by taking the second equation and dividing by the first equation, because the alphas would cancel and one of the betas would cancel. I could say alpha beta squared divided by alpha beta, which simplifies to just beta, equals M2 minus M1 squared divided by M1. That's what beta is. And now solve for alpha. For example, use the first equation, combine them. Alpha is going to be M1 divided by beta, but I replace beta with M2 minus M1 squared divided by M1. I'm dividing by a fraction. I can multiply by its reciprocal. This is the same as, I've not made a mistake, M1 squared divided by M2 minus M1 squared. I'll check the book and see if I got that right. Chapter 7. Near the beginning. Example 7.7.2, 7.2.2. It's page 230. We're essentially doing the same thing, and yes, this is correct. However, you don't quite stop there. We're almost done, but we don't quite stop. Yes, we solve for alpha and beta, but we now do not call these alpha and beta. We call them alpha hat and beta hat. Why? Because alpha and beta are population parameters, they're numbers. These M things, these functions of M1 and M2 are not numbers. They're random variables. They're statistics. So use the hats to emphasize these things are really statistics. So the final step when you do this kind of thing is to put hats above your parameters to emphasize we now want to think of these as statistics instead of numbers. These are statistics. They have distributions, they have PDFs, they have CDFs, they have means, etc. Let's apply this now to the chutes and ladders. So you've got it written down. Alpha hat is m1 squared divided by m2 minus m1 squared. And again, m1 could get replaced by x bar. It'd be the same formula. And beta hat's m2 minus m1 squared, all divided by m1. Have that written down because now I'm going to the computer. Let's calculate their observed values based on these data, right? We do want to ultimately apply the statistical theory. So we ultimately do want numbers. The mean, what was the data set called? It was called number of spins data. That was 29 something. That's our observed value of M1. Maybe I should call it M1, little m1 because it's an observed value. What's little m2? That would be the observed value of this natural estimator, M2, add up the observed values of the data values squared and divide by n. Average the squared data values. There's a few different ways that could be done in Mathematica here. I think this works. I think I can actually do number of spins data squared. In Mathematica, that will work. In other programs, it might not work. I believe this should square all those numbers that are all in the 10s, 20s, and 30s, etc. So we should get numbers here that are in typically above 100, most typically above even 400. Sometimes in the thousands, sometimes less than 100. So there they are, and then I could average those, mean squared data values. 1084.93, that would be our observed value of M2. Another way I could find this is to use this fact again. That's true for the theoretical variance. It would also be true for, let's see, would that really work? Yeah, it would. I should be able to take the, essentially solve for e of x squared and think of it in terms of statistics rather than population parameters by adding the mean squared to both sides. So I should be able to also compute it by doing the variance of the number of spins data minus the mean, no, plus the mean squared. Different. Okay, I'm not sure. That could be because it's using the population variance or the sample variance rather than, it might be dividing by n. No, okay, it is dividing by n minus 1. I know it is in Mathematica. I looked it up. Yeah, I think it's related to the fact that though that here we're dividing by n for M2. So it is slightly different. So I need to do it the other way. I need to do it the first way. So our observed value of alpha, hat, I should say. What should I call it? Alpha hat observed, maybe. according to this formula, should be m1 squared divided by m2 minus m1 squared, little m1 and m2. Hopefully it's close to maybe 4 or 5 or 6 or 7 something, 4.46. And beta hat observed using this formula here should be m2 minus m1 squared all divided by m1. And when you multiply those, alpha hat observed times beta hat observed. What should we get? We should get the mean. 29.771. 29.771. And if I do alpha hat observed times beta hat observed squared, that should be the variance, 198.621. I didn't compute that here. Variance, spins data. Okay, 198, it's not matching, let's see. Not matching exactly, probably for the same reason as before. So using these things is not necessarily providing unbiased estimates for the variance, at least. It's not the same as using this formula. It's using a different estimator for the variance that's not unbiased, it's biased. That's what happens sometimes when you do when you're trying to think about the theory of estimation. Sometimes you get estimators that are unbiased, and sometimes you get estimators that are biased. Unbiased seems better, but it's not the only ideal quality in an estimator. There are other qualities like consistency and other things that we'll see on Thursday and next Tuesday. The end of chapter 7 you should also read as well. I haven't had time for it today. Study it. Reminder what it gets into. It gets into, well, the method of maximum likelihood, which we will talk about on Thursday. Maximum likelihood estimators. Also gets into some pretty important stuff related to finding distributions of sums of random variables, for example, this theorem. To find the moment generating function of the sum of two independent random variables, you multiply their moment generating functions. And you may remember from problem stats that when you combine that theorem with the fingerprint theorem, it allows you to identify distributions of random variables. And in particular, the distribution of x bar. We know its mean and its variance, but what's its actual distribution? If x is normal, x bar turns out to be normal. And more generally, even if x is not normal, the central limit theorem implies that x bar is approximately normal when n is large. But as one quick reminder, this theorem as stated in this book is not really a theorem because it's not stated in a precise enough form. They did it for a good reason. Stating it too precisely is just too difficult for our purposes. And the central limit theorem is a big deal. Okay, have a good day.